In this video, we're going to walk through two examples of ice tables. The first will be finding equilibrium concentration, and the second will be using the reaction quotient. In our first example, we will be finding equilibrium concentrations of all species in a reaction. So a mixture consisting of 0.201 moles of hydrogen gas and 0.201 moles of iodine gas is brought to equilibrium at 500 degrees Celsius in a 4.5 liter flask. What are the equilibrium amounts of hydrogen, iodine, and hydrogen iodide if Kc equals 50.2 at 500 degrees Celsius? The first thing we need to do is set up our equilibrium expression. So we have hydrogen gas, H2 gas, plus iodine gas, I2 gas, in equilibrium, and we need 2 hydrogen iodides to balance that out. Okay, so that's our equilibrium expression. Now we can build our ice table. So I'm just going to move this up a little bit. So we'll write I, C, E down the side. We need equilibrium concentrations, and we're given amounts in moles, so we need to divide by the volume of the flask. Our initial concentration of hydrogen is 0.045 moles per liter, and the same for iodine. Because we're not told that any hydrogen iodide is initially added, its initial concentration will be 0. Because we don't have any product to start, the change on our product side must be positive to reach equilibrium, and the change on our reactant side must be negative to reach equilibrium. So this will be minus x for both of these. The coefficient is 1. The coefficient is 2 for hydrogen iodide, so the change will be positive 2x. So our equilibrium concentrations will be 0.045 minus x for both hydrogen and iodine, and it will be 2x for hydrogen iodide. So we can set this up into our equilibrium expression. So Kc equals the concentration of our product, so hydrogen iodide raised to its coefficient, over the concentration of our reactants. Okay, and we can plug in the numbers we know. So we know that Kc is 50.2, and over here we'll have 2x all squared for hydrogen iodide. And then because hydrogen and iodide are the same at equilibrium, we can simplify our denominator here. So instead of writing the same expression twice, I'm going to write 0.045 minus x squared. And that's going to allow me to simplify this without using a quadratic formula. So I'm going to take the square root of both sides of this equation. That's going to allow me to cancel out these exponents. So now I can rewrite my expression as the square root of 50.2, which is 7.1. So 7.1 equals 2x over 0.045 minus x. So to rearrange this, we're going to bring the 0.045 over to this side of the expression. And we get 0.32, so I'm rounding when I'm writing, but not in my calculator, minus 7.1x equals 2x. So now I'm going to take this 7.1x and bring it to this side of the equation, and I'll be left with 0.32 equals 9.1x. And so I'm going to divide both sides by 9.1 to solve for x, and that will let me figure out that x is equal to 0.035 moles per liter. Now the question is asking for the equilibrium concentrations. So the equilibrium concentration of hydrogen gas is equal to the equilibrium concentration of iodine gas, which is equal to 0.045 minus x. And so since we know what x is, we can plug in that number and we get 0.0098 molar. We can do the same for the concentration of hydrogen iodide. And so that equilibrium concentration is 2x, which is 0.0696, so 0.070 molar. For this next problem, we're going to be doing something a little bit different. So we have carbonyl bromide, COBr2 gas, can be formed by reacting carbon monoxide with bromine gas. A mixture of 0.400 moles of carbon monoxide, 0.300 moles of bromine, and 0.0200 moles of COBr2 is sealed in a 5-liter flask. So calculate the equilibrium concentrations for all gases given that Kc equals 0.680. First things first, we need to write an equilibrium expression. So we will have carbon monoxide gas plus bromine gas forming carbonyl bromide, COBr2 gas. So that's our balanced reaction, and we can build our ice table down the side. ICE. Now these are given in moles, so once again we need to divide the moles by the volume in order to get our molar concentration. And we get 0.0800 moles per liter carbon monoxide, 0.600 moles per liter bromine, and 0.00400 moles per liter carbonyl bromide. In this reaction, unlike in the previous example, we start with some amount of product. And what that means is we can't tell just by looking if our reaction will shift right and form more products or shift left and form more reactants. So we need to do a little bit of math to start. So we're going to calculate something called the reaction quotient. So this is given by the letter Q, and it's calculated the same as the equilibrium constant. So products over reactants. But we're going to use our initial concentrations rather than equilibrium concentrations. So we're going to have 0.004 moles per liter divided by 0.08 moles per liter and 0.06 moles per liter. And our reaction quotient is equal to 0.833. Now, this is bigger than our K value that's given in the question. And what that means is that we have too many products present for equilibrium. So our reaction is going to shift to the left, meaning we're going to make more reactants and we're going to use up the products that we have. So going back to our ice table now, what that means is that for our change, this is going to be a positive change and this is going to be a negative change. So we'll have positive here, positive and negative. And all of our coefficients are 1, so this will be x, x, and minus x. And so our equilibrium concentration will be 0.08 plus x, 0.06 plus x, and 0.004 minus x. To solve this reaction from here, you would need the quadratic formula, so we're not going to go any further. But if you're ever given a problem where you're given the initial concentrations of both reactants and products, you must test for Q.